Alright, and this first figure really shows what I mean. It compares the new method called Region-Adaptive Latent Upsampling, or RALU, against other techniques. These methods speed up image generation using either temporal acceleration, which is about reducing the number of processing steps, or spatial acceleration, which works on lower resolution data. Now, looking at the competing methods, you see these visual errors, or artifacts. The bear's fur becomes blurry, and the bathroom sink gets distorted. But the images from Region-Adaptive Latent Upsampling stay incredibly clear, preserving fine details even at a 7x speedup. So, what are these artifacts I mentioned? Well, this next figure shows the exact problems that Region-Adaptive Latent Upsampling is designed to fix. These issues pop up during something called latent upsampling. That's when the model tries to increase the resolution of its internal, compressed idea of the image. On the left, you see aliasing artifacts, these jagged linear patterns around the cowboy's hat and the glass. On the right are mismatch artifacts, which look like weird grid patterns or just random noise, like on those train tracks. These are the specific errors the new method avoids. So how does the method actually prevent those problems? Well, this diagram lays out the core idea, a clever three-stage process. First, it quickly generates a rough, low-resolution version of the image to capture the main structure. Then, in the key step, it uses canny edge detection, a classic computer vision technique for finding outlines, to identify and upsample only the most critical edge regions. Finally, it upsamples the rest of the image. To keep everything stable during these resolution changes, it uses something called noise time-step rescheduling with distribution matching, which carefully manages noise levels to prevent artifacts. Okay, so this table gives us the hard numbers, testing the method on another powerful model, Stable Diffusion 3. It compares Region-Adaptive Latent Upsampling against other techniques at 2 and 3 times speedups. We're looking at image quality and how well the image matches the text prompt. For quality, a key metric is FID. That's Fréchet inception distance, which measures realism, so lower scores are better. And you can see, at a 3 times speedup, the new method achieves the best FID score, far better than the others, while also being the fastest. And this next table shows the results for that other big model, Flux.1dev. Here we see a direct comparison at both a 4 times and a much more demanding 7 times speedup. At 7 times the speed, the difference is just massive. The competing methods really struggle, with one getting a Fréchet inception distance score over 150, which is very poor. But the new method, Region-Adaptive Latent Upsampling, keeps its score at a strong 28.68. It also maintains great text alignment, which measures how well the image matches the prompt, while the others completely fall apart. So this table explores if we can push the speed even further. The authors combine their method with another trick called caching, which is a technique that saves and reuses previous calculations to avoid redundant work. And the results are great. When you add this caching to that 7 times speedup we just saw, it pushes the total speed to nearly 8 times. This extra boost comes with almost no drop in image quality. The Fréchet inception distance score stays very strong. This shows these different speedup approaches can be stacked together. So to wrap things up, this work on Region-Adaptive Latent Upsampling presents a really clever, training-free way to accelerate diffusion transformers, which are these powerful but computationally heavy models for creating images. The key is its focus on spatial acceleration, intelligently changing the image resolution during generation. By using a sophisticated noise rescheduling method, which aligns the generation process with something called the original rectified flow trajectory, it avoids visual errors and achieves massive speedups without sacrificing quality. It's a great example of optimizing smarter, not just harder. Thanks for tuning in. I'm Alex, and this has been the AI Research Roundup.